Hello everyone, welcome to Probability and Statistics for Data Science. Today I'm going to explain my philosophy for teaching probability and statistics to data science students. I will also provide an overview of topics in probability and statistics that, in my opinion, every data scientist should know. Let's get to it. I'm going to provide an overview, but let's start with my philosophy, which I have developed over 10 years teaching probability and statistics to data science students at New York University. I strongly believe that it's important to provide a description of probability and statistics that is self-contained and therefore includes comprehensive theoretical but also intuitive explanations, that is useful in practice, and for this I think it's completely critical to include real-world data examples for every topic. And if there's a topic where we cannot find a real data example, then that might be an indication that it's not super important. And finally, I think it's really important for the description to have a logical flow. Let's see what I mean by this. I think that probability, statistics, and causal inference should be taught together, intertwined between them, because otherwise, if we do as in traditional approaches where they first cover all of probability and then cover all of statistics and maybe at the very end talk about causal inference, the following happens. When learning probability, students get unmotivated because they don't really see the point. Why is this important for data science? Then, when you reach statistics, students have forgotten some of the probabilistic concepts that were critical to understand some statistical concepts, because why would they have known that those specific concepts were super critical? And finally, by the time you reach causal inference, there's these other probability concepts that were very important that need to be reviewed. At least this was my experience both as a student and when I taught probability and statistics for data science at first, where I also separated probability and statistics. So, motivated by this philosophy, I have written a book which contains materials developed over the last 10 years. The book is going to come out in a few days, so by the time you see this video, probably it will already be out. It will be published by Cambridge University Press. There's also 115 YouTube videos where I try to provide as much intuition as possible about the material in the book. There's 200 exercises with solutions. There's also 102 Python notebooks that contain all these real-world examples that I believed were super important, so I put them all in the book, that use 23 real-world data sets, and all of this, including a free preprint of the book, is available at the website ps4ds.net. All right, so now I'm going to provide an overview of the topics that I believe are critical in probability and statistics for data science, and I'm going to structure them in 12 themes that correspond to chapters in the book. These are probability, discrete and continuous random variables, multiple discrete variables and multiple continuous variables, discrete and continuous variables, then averaging, correlation, estimation of population parameters, hypothesis testing, principal component analysis and low-rank models, and finally, regression and classification. So let's get to it. Probability provides us with the basic tools to be able to quantify uncertainty. This is all based on a theoretical framework, which is that of probability spaces, which looks super scary, but in reality just encodes common sense properties, so you should not be afraid of it. Conditional probabilities are critical to update models with new information, and we need to be able to estimate probabilities to do anything in data science, and we can do this through empirical probability estimation. And here you can already see that we bring up a concept from statistics, this is a statistical estimator, very early on, so that we can illustrate these concepts with real-world data. In the book, we use votes from the United States Congress. Independence and conditional independence are crucial concepts, not only in probability, but also in statistics and in machine learning. They do not imply each other. And a very interesting phenomenon is that probabilities often cannot be derived analytically, even if you have all the information at your disposal. You would never know this from most of the homeworks that we give in probability and statistics, but this often happens the case in practice. This is often the case in practice. Luckily, these probabilities can usually be approximated very well using Monte Carlo simulations. We illustrate this with an example where we model a basketball tournament in the Tokyo Olympics. When we are quantifying uncertainty, we often use random variables. Let's begin with discrete random variables. A mathematician will tell you that they are functions in a probability space, which sounds completely bananas unless you're a mathematician. In fact, as data scientists, we manipulate these variables with probabilities that we just predict from data and don't really worry about the underlying probability spaces. An analogy would be that as a data science, you're driving this car using the steering wheels that are the probabilities. You don't worry about what is going on in the complicated stuff that happens in the motor, which are the underlying probability spaces, which often we don't even define explicitly. However, it's important to know that they are there, so I do think that they have to be mentioned and described in a course on probability and statistics. When you want to actually manipulate variables within a model, you're going to have to estimate probabilities. So here again, we talk about statistics. You can do non-parametric estimation using empirical probabilities or parametric modeling based on distributions such as the geometric, the binomial, the Poisson that are fit using maximum likelihood to data. In the book, we use an example where we model Kevin Durant's free throw streaks. Continuous variables are very important to model physical quantities such as time, distance, weight, etc. Here the story is very similar. A mathematician will tell you there are functions in a probability space, but a data scientist will tell you, don't worry, you can just manipulate them using probabilities that you estimate from data, and that's kind of the end of the story. It's a bit trickier to define these probabilities for continuous variables. We either use the cumulative distribution function and quantiles. Here you can see the CDF and the quantiles of the height in a real population, or we use probability densities. In order to estimate these quantities, here again we introduce statistics because we needed to be able to manipulate data. We can apply non-parametric modeling, computing the empirical CDF or the empirical quantiles, or estimate densities using the histogram and kernel density estimation. Alternatively, and this is an example where we compute the kernel density estimate of inter-arrival times at a call center, at a real-world call center. Alternatively, we can apply parametric modeling where we fit parametric distributions such as the exponential or the Gaussian to data using maximum likelihood. And here is an example where we fit an exponential to the same data. Finally, it's important to know how to simulate continuous random variables. For example, if you want to apply Monte Carlo estimation, and we can achieve this using inverse transform sampling. Of course, models are not only going to have a single variable, they're going to have multiple variables. If you want to manipulate multiple discrete variables, you can use joint probabilities, like the ones that you see here between two locations in Oregon. These are probabilities that it rains in the locations, or snows, so it's precipitation. You can use marginal probabilities to isolate the behavior of one individual variable. There you can see the probability that it rains in one of the locations. You can see that the probability that it rains, which corresponds to 1, is pretty low. And conditional distributions. There you can see the conditional distribution. If it rains or if there's precipitation in the other location, suddenly, boom, the probability is much higher. Here already, I believe it's important to talk about causal inference because these conditional probabilities do not necessarily reflect causal effects. And to understand that, we need to introduce the framework of potential outcomes, talk about randomization under which they would represent causal effects, mention confounders that can completely distort observed conditional effects, and even lead to Simpson's paradox, which could lead you to think that Courtney Lee was a better three-point shooter than Steph Curry, precisely in the year where Steph Curry won the MVP, won the NBA, and was widely regarded as the best three-point shooter in history. And another very interesting phenomenon that is super important in practice is that unless variables are very few, independence assumptions or conditional independence assumptions are absolutely critical to ensure tractable estimation, because otherwise it's impossible to estimate all the dependence between random variables due to the curse of dimensionality. And this is why in machine learning we make conditional independence assumptions all over the place, because otherwise it's impossible to compute anything from data. An example of this is naive Bayes, a method for classification that we apply to predicting political affiliation from votes in the US Congress, and also Markov chains, which enables us to model time-structured data in a tractable way, also applying conditional independence assumptions. You might also want to model multiple continuous variables, and in that case, you will use joint densities, the joint density of the temperatures in Versailles, Kentucky, and Manhattan, Kansas. I was very amused by these names. This is the temperature in only one of the stations, so this is the marginal density, and it completely changes if we have information about the temperature in the other station. This is the density, the conditional density, if it's very hot in the other station. In the other station, you can see that the probabilities are the probability of a higher, basically the density is concentrated at a higher temperature. Let me get that right. You can apply non-parametric modeling here using kernel density estimation, but this is going to start becoming problematic when you have a lot of variables. Instead, you could also use parametric modeling where you fit a Gaussian distribution, a jointly Gaussian distribution to the variables, such as in this anthropometric data. Anthropometric data is just a fancy way of saying that we have the height and the foot length of people in a population. And if you want to simulate multiple continuous variables, you have to be a little bit careful, because you have to make sure that you use the conditional distributions of one variable given the other. In probabilistic models, you almost always have both discrete and continuous variables. In order to manipulate them, you're going to have to use their conditional probabilities or their conditional densities, depending on whether they're discrete or continuous. And for this purpose, parametric mixture models are very useful. We can use them for classification. This is called Gaussian discriminant analysis, here applied to the diagnosis of Alzheimer's disease from the volumes of two brain regions, or you can apply them to clustering, as in Gaussian mixture models. And here you can see some clusters of NBA players according to their rebounds per game and their assists per game. In Bayesian models provide a very useful framework to manipulate discrete and continuous variables. We illustrate this by analyzing a poll in Pennsylvania in 2020 in order to predict the outcome of the election in Pennsylvania and assign some uncertainty to our prediction. Bayesian models can also show us how not to predict an election, and this is an example that I use to show that independence and conditional independence assumptions are absolutely critical in modeling and can really change your results, as can be illustrated by the terrible predictions that were carried out before the 2016 election between Clinton and Trump. We use averaging all over the place in data science, and because of this, it's critical to define an averaging operation that we can apply to random variables, and that averaging operation is the mean. Then we call the sample mean what we do to estimate the mean from data, but that's just an average. And here you see the mean temperatures in the United States, which show you that it's much warmer in the south than in the north, as you might imagine. The radius of each marker is proportional to the mean of the temperature at that location. The mean has very important properties such as linearity of expectation and also its sensitivity to outliers. Here an alternative would be the median that is not as sensitive. And the variance and the sample variance allow us to quantify the average difference between a random variable or, in the case of the variance, and some data in the case of the sample variance from the mean. It's the squared average deviation. If we take a square root of that, we get the standard deviation that gives us an estimate of the average deviation from the mean. I feel that I said this in a bit of a convoluted way. So here you can see some standard deviations of temperatures in the US. The trend is very different to the one that we see in the mean temperatures. There's much more variability in temperatures inside the US away from the coast and in the Northeast. Average iterated expectation, allows us to compute averages using conditional probabilities, and the conditional mean allows us to solve the regression problem. In fact, it's optimal for regression. Here is the conditional mean of the ratings of a movie called Independence Day based on the ratings for another movie called Mission Impossible. Here's the conditional mean of the temperature at a certain location conditioned on, I think it's either Versailles or Manhattan, conditioned on the temperature in Corvallis, Oregon. Here again, it's important to emphasize that conditional means, or equivalently the average treatment effect, which is computed using conditional means, does not reflect a true causal effect if there are confounders, and we have to learn how to adjust for them. And that's in the realm of causal inference, but I like to embed it when we are talking about the mean, because it's just so important to understand when statistical quantities reflect causal effects and when they don't. This brings me to correlation, which also has an interesting connection with causal inference that I will explain in a moment. Correlation captures the average linear relationship between two variables, and we quantify this using the covariance and the correlation coefficient. The sample correlation is how we estimate correlation from data, and this allows us to perform simple linear regression, which captures the linear relationship between two quantities. Here it's rebounds per game based on height. I've also included a nonlinear estimate, which is computed via the conditional mean, and assists per game compared to height. As you can, if you know something about basketball, you will know why the trend is increasing when we're looking at rebounds and the trend is decreasing when we're looking at assists. And this is for data from the NBA. Correlation has a beautiful geometric interpretation where random variables are vectors. The length of that vector is the standard deviation of the random variable. And if you consider the angle between the vectors, the cosine of that angle is the correlation coefficient, so that when the angle is 0, so that the cosine is 1, that means complete dependence between the two variables, so the two vectors are on top of each other. And when the angle is 90 degrees, so that the cosine is 0, that means that the two vectors are orthogonal and the variables are uncorrelated. And correlation does not imply independence because there can be non-linear dependence between variables, and correlation definitely does not imply causation. In fact, unemployment is negatively correlated with temperature in Spain. That doesn't mean that if next month there's a heat wave, we can expect the unemployment suddenly to go down. Estimating population parameters is a super important problem in many scientific domains. For example, you might want to estimate the prevalence of a certain disease in a population. And we can achieve this by random sampling, where we pick just some random individuals of the population and we aggregate the, we measure them and then we aggregate this data. The bias tells us how the corresponding estimator, like the average error of the corresponding estimator, and the standard error tells us how much it deviates from its mean. It turns out that when we apply this to averaging, to the sample mean, this is an unbiased estimator where the standard error becomes smaller and smaller as the number of data grow, and that's called the law of large numbers, and it's super important in both probability and statistics, but there are some exceptions where it does not hold, and it's important to understand why, because some of its underlying assumptions do not hold. In the case of height estimation, as in this graph here, it does hold. You can see that the estimator is converging to the true population height, population mean of the height. The law of large numbers tells us how an average that our estimate of an average becomes arbitrarily accurate if we gather more and more and more and more data. The central limit theorem tells us that the behavior of that estimator is actually Gaussian around its mean, and you can see an illustration of this phenomenon here, where I show you the distribution of averages computed with a certain number of data points, and as the data points increase, our estimate of the average has a Gaussian distribution. This is critical in statistics, where it enables us to compute confidence intervals that quantify our uncertainty about parameter estimates. Here are some confidence intervals for the mean in a certain population. An alternative to compute confidence intervals is bootstrapping, which is a computational approach that is based on resampling the available data. Hypothesis testing enables us to evaluate scientific hypotheses based on available data. Basically, the way this works is we take a devil's advocate approach where we say, I don't think anything interesting is happening. That's called the null hypothesis. And then we use the p-value to quantify how likely it is for this null hypothesis to hold. And if that probability is very low, then this is evidence in favor of our original hypothesis. We apply this framework to study the question of whether Giannis Antetokounmpo was shooting free throws better at home or away, because when he was away, people were basically yelling 1, 2, 3 to try to throw him off. This is back when they played the final of the NBA against the Phoenix Suns, I believe. We can apply parametric testing to perform hypothesis testing. We can use this to show that controlling the p-value ensures us a statistical significance in the sense that it controls the false positives. This parametric framework also enables us to determine to what extent a test enables us to find true positives, and that's the power of the test. Surprisingly, you can also do all of this stuff without a parametric model, and that's called non-parametric testing, and one of the most popular models for this is called the permutation test, which we also apply to the example with Giannis Antetokounmpo. Multiple testing is extremely important in real applications, because when you apply several hypothesis tests at the same time, one of them might seem statistically significant just by chance. In this case, it's the one from this guy who's very happy, but that doesn't, the guarantees provided for hypothesis testing for a single test no longer hold. It's also important to understand the relationship between hypothesis testing and causal inference, because they are complementary. They play complementary roles when we analyze data. Finally, we should not only rely on p-values when we're evaluating the importance of a scientific observation, because the p-values don't necessarily reflect practical significance. Also, this induces publication bias and the temptation of p-hacking. Principal component analysis enables us to analyze data which has multiple features and is therefore high dimensional. The covariance matrix of a random vector captures the variation of different linear combinations of the random vector. Analogously, the sample covariance matrix of a data set captures the sample covariance of any linear combination of the data within of the different features within the data set. From that, we can extract the directions of maximum variation by performing an eigendecomposition of either the covariance matrix or the sample covariance matrix. These directions of maximum variation are called principal directions. The components of either the random vector or the dataset in these directions are called the principal components, and we can use them for dimensionality reduction, as I will show in a moment. This is the direction of maximum variation in a dataset of Canadian cities, basically the geographical location of the Canadian cities, and these are the directions of maximum variance for a data set of faces. And as I said a moment ago, you can use the components corresponding to these directions to perform dimensionality reduction for visualization or other downstream tasks. Low-rank models enable us to process matrix-valued data, usually applying tools such as the singular value decomposition and truncating this decomposition to obtain a low-rank model. These ideas are very useful for matrix completion for collaborative filtering, where we try to estimate the preferences of different users from preferences of other users and their own. Here you can see this as a matrix which has users and, for example, movies, and we're missing some of the movie ratings. We want to predict them. Well, what we can do is we can fit a low-rank model to this data that has a small enough number of parameters that we can fit it using the observed data, and then use that, like basically expand the matrix and predict the missing ratings. This is super useful, in fact, for movie rating prediction, as was illustrated by the Netflix challenge. Finally, we reach regression and classification. Linear regression is extremely important. It's usually based on linear minimum mean squared error estimation from data. This is implemented using ordinary least squares to find linear models such as the one you can see there, represented by that plane, where we try to predict mortality from household income and also smoking. It's critical to understand when these linear models provide causal insights, and this is very connected to the reason why correlation cannot be does not imply causation, and also provides a solution, because if there is a true linear effect, if you include include all the existing confounding factors into a linear model, you can actually adjust the distortion in correlation caused by those confounding factors. If you have a lot of variables and you fit a linear model, you will probably run into overfitting, which can be addressed using regularization techniques such as rich regression or the lasso, which enables you to perform sparse regression. You want to solve a classification problem instead of a regression problem, you can apply logistic and softmax regression, which feed linear models of the data into link functions that map them to probabilities. There you can see an example of logistic regression applied to Alzheimer's diagnosis. Non-linear methods for regression include regression and classification trees, which are great and very interpretable. There you see a regression tree that was fit to some temperature data, but unfortunately these models tend to underfit if they're small and overfit if they're large. A smart solution to this that has been spectacularly effective is combining combining many of these models, either by bagging random forests or boosting. You lose interpretability, but performance is usually much, much better. An alternative approach to fit nonlinear regression and classification models is neural networks and deep learning, which has become incredibly popular in the past 10 years. There you can see a small network that was fit to the same temperature data as the regression tree on the left. And that's essentially all I got. Hopefully this illustrates my philosophy, which was gained over the last 10 years teaching probability and statistics for data science. I do believe that you need to provide a description of probability and statistics that is self-contained and is justified theoretically, but also contains a lot of intuition, is useful in practice. So I believe in using a lot of real-world examples to illustrate every topic from the beginning, which requires you to provide, actually this is a previous version of the slide, I'm sorry for that typo. There it should say that it should have a logical flow, and that probability and statistics should be taught in an intertwined way, also together with causal inference, and then that enables you to provide real-world data examples from the beginning. And that's it. Hopefully you will find this useful and you have all the materials on the website. Thank you very much.